Hi, everyone. I'm Adam Archer, and this is Joe Pym. And we're really excited to be here today to talk to you about building scalable applications on the Shopify platform. Our team is responsible for some of Shopify's largest sales channel applications. This includes Instagram, Amazon, Facebook, Pinterest, and Facebook Messenger. We've experienced the launch and growth of all of these channels, and some of them have scaled to hundreds of thousands of active merchants. We want to stress that we build all of these sales channels using the exact same API and platform that all of you build your apps against. So a lot of the principles and practices that we've learned in scaling our apps may be directly applicable to your problem domains. What we're going to do in this talk is take you through a fictitious case study of what it would look like to build a new sales channel in which basically everything that can goes wrong does. We're going to highlight 6 problems that we've encountered. Some of them are exactly as they went down. Some of them are slightly exaggerated for the sake of example. And we're going to show you how we adjust the architecture of our app to accommodate the new challenges that we're facing. We believe heavily in using monitoring and charting to track the performance of systems in real time. And with that in mind, the way that we're going to structure the talk is that we're going to introduce you to each new problem first from the perspective of what you'll actually see in your charts and what's actually going on in the systems, and then take you through the process of investigation and what's happening and how we address it. We're drawing from our experiences building sales channels, but it's important to note that a lot of these practices can apply to a wide variety of apps, whether you're talking about a t-shirt printing app, a marketing app for the new platform, or a fulfillment service. What matters is that you take what applies most to your domain. I'm sure you're all very familiar with this by now, but we'll be using the app for the live Q&A. Go to the Q&A section, enter the code UNITE, and pick track 1.
So, I'd like to introduce you all to Marketplace, the new, hottest place to shop online, also fictional. They want a channel on Shopify, so they've contracted us, an agency, to build it. We're going to sit in between Shopify and Marketplace, talking to both APIs, dealing with webhooks from both places. It looks a bit like this. You have merchant traffic coming into the Shopify app. You have webhooks coming in from Shopify. And then we're making requests out to Shopify and to Marketplace. It's worth noting, as Adam said, while this is a sales channel, this Marketplace could be any API. We could actually be talking to a physical printer, printing T-shirts. The principles still apply. And take this talk with a grain of salt. These patterns are general. Pick the ones that make sense for you. If it doesn't make sense for you, great. Look at the principle and think of how you can handle it. Let's get started. Your app's launched. Congratulations. Huge success. Marketing went really well for it. You're getting merchants installing it. Things are looking good. But this graph is your page load time. And bad App Store reviews are arriving constantly. This app is too slow. I make my morning coffee while I upload my products. What can we do about it?
So relatively speaking, this is actually a pretty good problem to have. We have too much success, and our app can't actually handle the load. We just don't have enough resources. So this is our first major problem. First, let's look at how our app is architected today. We have a basic web server and a database. Our web server is a Ruby on Rails app, and our database is running MySQL. The problem here is that merchant traffic is slow, and the bottleneck is simply the web server. We don't have the capacity to handle the requests that we're receiving. So this is a relatively easy problem to solve. We just need to add resources. The easiest way to do that is to deploy a bigger server. Add more RAM, add more CPU, add whatever it is that's bottlenecking your app. This is called vertical scaling, and it'll work to a point, but it's a bit of an anti-pattern because you hit physical limits very quickly and can't actually scale this way. So instead, we're going to introduce the concept of a worker-server cluster, and we're going to use the principle of horizontal scaling. What this means is instead of deploying a bigger server, we just deploy more small servers. This is pretty standard practice in the industry today, and many of you are likely completely familiar with this concept. It does have some implications on the structure of your app. First, you're going to need a load balancer to decide which server should handle each of the requests, something that sits outside of that web server cluster and balances the load accordingly. Additionally, your app needs to be stateless. Your web servers can't know anything about the requests that have happened before because they could be handling any individual request. We won't go into much more detail here, but there's lots out there if you aren't familiar with these concepts. Luckily, we deployed to the Google Cloud, which handles the load balancing layer for us, so it's really easy for us to simply deploy more web pods and scale up our app. So that's what we do. So we've used horizontal scaling to improve our response times, our merchants are happy, our app is back on track, and things are looking great, at least for a while, until we see the exact same pattern occur, only worse. So what's actually happening here?
We had a bottleneck. The bottleneck was our resources. Cool, we upsized. We solved the bottleneck. But what's happened is we've just pushed it down the line. The marketplace APIs we're talking to are now struggling in the same way that we were struggling before. And their response times are rising. Now, up till now, we've built the app synchronously, which means that when a merchant presses the button to upload a product, we talk to the API directly. We send that request straight to the marketplace. And because of this, when the marketplace goes slowly, our merchants see that. They see that slowdown, and they feel it. And to them, they don't know it's the marketplace, so they are complaining that we haven't fixed the problem. This is our second problem. What do you do when the APIs you're talking to are slow? This is our current system. You can see on the top right, we have slow calls to the marketplace, and on the bottom left, the merchants are feeling the pain. This is because of those synchronous requests we were talking about. So the solution here is pretty obvious. Don't make the request synchronously. It's much better to acknowledge the merchant has pressed the button and give them immediate feedback than it is to let them spin, where they don't know whether your server has received the request, what's happening, and they're in this kind of indeterminate state. Let me just introduce 3 new concepts. The first is called a job. A job is a unit of work that we need to do at some point in time. The second is a queue. A queue holds jobs until we're ready to process them. And speaking of processing, we have a worker server. A worker server takes those jobs off the queue and actually executes them. The API calls in this context are being made from the worker. For us, we use Redis for the queue and Sidekick for the job and worker mechanism. This is what the new architecture looks like. It looks a bit scarier, but it's really quite simple. On the right-hand side, we have the worker server cluster, similar to the web server cluster we had before. And these worker servers are responsible for making all the API calls. Now, when you have a webhook coming in, instead of it making a direct API call, it instead queues a job. That job sits in the queue until a worker has free capacity, and then we process it. There is another important point here, though. These requests, obviously, are no longer happening immediately. This means that your front end, your user experience, needs to understand the concept of pending. You need to know, the merchant needs to know that this click isn't active yet. It will be soon, but it's not yet. And usually, this comes with some kind of feedback mechanism, some way of telling the front end that, oh, we're done, product's ready. Examples might be polling, WebSockets. There's a lot of front-end tech to do this work, but be aware that if you're solving this problem, it's not as simple as slapping a background queue in and calling it a day. You need to actually update your user experience to account for the fact that things are being delayed. And finally, there's this point at the bottom, front-end requests. And this is important because there is some types of request that we can't background. To break away from the marketplace example for a second to our own experiences, let's talk about Facebook. When we're building the Facebook channel, and you want to connect, the merchant wants to connect their Facebook page. We want to give them real-time feedback. If the page doesn't connect for whatever reason, they need to know about it. They don't want to sit there saying, might be there, give us 5 minutes, because merchants are busy, they'll just walk off. And then we don't have the chance to tell them to correct it. And in cases like this, you just have to eat the pain with slow requests. Maybe you set up a few user expectations, but that's just what it is. Awesome. Backgrounded our API calls. Now, we can receive loads of traffic without our merchants feeling the pain. Let's have a look at what that looks like on a graph. This graph represents requests over the course of a day. The red section at the top is failing requests, and it's happening during the times of our peak activity. And what's happening is, when we're in one of those red sections, users can't onboard. Those front-end API calls we were talking about, the ones we needed to make, those are failing. And users merchants are making 1-star reviews. They're saying, this app just doesn't work. Installed it, pressed go, nothing happened. Everything broke. What's happening?
We've hit our third major problem. Again, we've grown too much for the system, and it can't handle it. What this is actually caused by is firing too many requests to that marketplace API. It's applying a rate limit to us, and we're exceeding it. And our app isn't actually designed to handle it. Most of you are probably familiar with the concept of rate limiting, but the basic principle is that the API imposes a maximum number of requests that we can make during a given period of time. There's a bunch of different algorithms, but I won't go into them. What's happening here, as Joe said, is that onboarding is failing because our API rate limit is saturated, and those synchronous requests aren't working. Let's take a look at what this actually looks like in our architecture and figure out how we can solve it. So first, our workers are working as fast as they can to upload products for our merchants. And during those periods of peak activity, there are so many jobs, and we're working so quickly that, like I said, we exhaust that rate limit. During that period, none of those onboarding calls are working. And that's actually during business hours, right? That's during our core period. It's the worst possible time for onboarding to be broken. The good news here is that this is not actually impacting our background work. When those HTTP requests fail, that in turn fails the jobs, which is causing them to enter the retry queue, and they'll stay there until that peak activity subsides and they're able to go through as expected. So at least the system is working for our existing merchants, but it's still not very efficient. We're making a bunch of requests that we know are going to fail. We're wasting a bunch of resources doing that work. And of course, onboarding is broken, which is terrible. So how do we improve? We're going to introduce the concept of throttling. Effectively, we are being throttled by the back end, and we just need to build our app to have awareness of that to ensure that we conform to it properly. There are a bunch of different ways we can do this, and in fact, our sales channels actually do it in different ways. This is an important point where you need to consider the nature of the APIs you're calling, the structure of the rate limit, and other factors in your app to decide the best way to approach this. I'll take you through 2 examples. Some of our apps actually instrument this at the client libraries that are making the HTTP calls. So that means low level in the jobs, right before we make the HTTP request, the piece of code that makes it knows about how many requests we've made and just throws an exception and doesn't make the request before it actually goes out. This, like with the previous pattern, causes the job to fail, causes it to re-enter the retry queue, and we actually leverage the retry queue to work off that work during those periods of lower activity. In this case, you'll notice we're showing the throttle between the worker cluster and the queue. And with this pattern, instead of pulling those jobs off and then let in the client, fail them, and re-enter the queue, what we're doing here is we're tuning our workers to pull the work at a rate that we know won't exceed our rate limit. This depends heavily on the nature of the work that's done. It means that it needs to be pretty predictable how many calls those workers are going to make in order for this to work, and it'll work for some domains but not others. So let's look at what this looks like in our overall architecture. We're now throttling our background jobs to ensure that we can conform to those API rate limits without breaking those onboarding flows. And what's important here is that because we need to leave room for onboarding, and because that comes from humans, that traffic is actually unpredictable. So it's important to ensure that the way you set up your throttle, you don't want it to consume 100% of your rate limit and leave very little room for bursts of activity from the front end. Again, this is all very domain specific. For us, we tend to set them to consume about 80% of our rate limit and leave 20% for spikes of merchant traffic. So we're able to handle our rate limit without breaking our onboarding through the use of throttling. But what happens if the marketplace goes down entirely? This chart's a little bit more complicated than the ones we've shown so far, so I'll walk you through it. The principles are pretty simple, though. The green line is successful API requests going out to the marketplace API, and the blue line is the size of our background queue. So what happens here is, as those successful requests start to decline, those jobs start to fail, they start to enter the retry queue, and our queues start growing very rapidly. Eventually, the marketplace hits complete failure, and our queue growth just skyrockets.
We've hit our fourth problem. But why is it a problem? Or more specifically, why is it our problem? Our app is running completely fine. It's just the APIs we're talking to are down. Surely we can just slap a status page up and call it a day. What is the implication of our queue growing rapidly? Let's, again, drop into a real scenario that we've hit, where we had an extended partner outage. We ran out of Redis space. We couldn't upgrade it quickly enough, and we were getting things coming in fast enough that we completely ran out of space. And when that happens, you can't put more jobs into the queue. And what that means is data loss. Because those webhooks you're sending, you're now losing them. You're losing the data they contain. So what we had to do, which is not what you want to do in the aftermath of an outage, was build reconciliation tools. We had to build tools that could go to the Shopify APIs and say, give us everything for every merchant that has updated in the last 48 hours. And then we had to compare that to our current state in the database and make sure things were even. On the bright side, at least our apps have these tools now, but it would have been really nice to not have to do that in the first place. We ran out because while the marketplace is down, our jobs are failing and retrying. Essentially, they're never leaving the queue. But we've still got webhooks punting more and more and more data into the same queue. If you can, first easy solution to this is increase your queue capacity. But at a certain point, that ceases to become an option, especially if you're getting hammered by traffic. The larger your queue is, the more downtime it takes to take the machine offline so you can upgrade it and put it back online again, or the longer you have to lock everything. And it's actually quite a hard problem to solve after a certain size. While you're small, cool, just keep throwing more money at it. But at some point, you'll hit a limit. Let's actually keep an eye on that queue. The jobs in the queue are now much smaller. That lets us last for a lot longer, because that's what we don't have control over. We don't have control over how long it takes the partner to fix it, so the more time we can buy, the more likely it is they'll come back online. In this context, what does smaller even mean? Up until now, we have been storing the full webhook body into the job. You never know when you might need that extra field. But now, we're storing just what we need. And if you have room in your Shopify rate limit, and I realize for a lot of people in the room that's a big if, just store the ID and pull the record from the API at the time things come off the stack. That said, we're still making a lot of requests that we know are going to fail. We know the marketplace is down. So what we're going to use is something called a circuit breaker. You can think of a circuit breaker kind of like a fuse. When you get a power spike, the fuse blows, and your house is protected. In our context, what happens is the circuit breaker usually sits at your API client level, and it monitors all the traffic and all the responses you're getting back. When you start getting a high percentage of failures, it cuts it. And it just stops all requests. Wait 5 minutes, bleed one through, see if it works. If it works, great. Open the floodgates, let things through. If it doesn't, stay locked down. Why do we care? Why is it important to us that we're not making failing requests? After all, it's an exception either way. It's ending back in our queue either way. First, we're being good citizens. Anybody who's had to deal with a situation like this knows that it's much harder to recover when you're getting slammed by traffic. And if every single partner that's integrating with you has a circuit breaker, your job is much easier, and you will come online much faster. But there's another side of this as well. In a lot of partner designs, the rate limit is on a different system. Sometimes the application system, in our case, maybe the unicorns or whatever, are down. But it doesn't mean that the system that is tracking the rate limit is also down. So we've actually hit this. We had a partner outage. We didn't have circuit breakers. And tons of requests come flying in. We fire them over. Partner comes back up. We start trying to post, and every single person is rate limited, because we've been hammering them over and over and over and over and over again with failing requests that are failing really quickly. And the systems that told us our available rate limit were down, but not the ones that were tracking how much rate limit we were using. So a circuit breaker can protect that as well, to make sure that when a partner comes back up, you're in a good state to actually keep sending them requests again. This is what our architecture looks like now. We have a queue change, more jobs in the queue, and we have circuit breakers over the API calls. The minimal data in the queue buys us time to recover from an outage, which is usually the most precious resource we have. And we're protecting our APIs and our rate limits with circuit breakers. That being said, let's welcome our first big plus store. We're getting a lot of webhooks now. See that first spike? That's 50,000 webhooks in a second. That's the entire product catalog for a big store being synced at once. And most of them fail. So Shopify waits a few seconds, then goes, hey, you missed these, and throws them all at us again. And they fail again, and again, and again. And all our monitors are screaming. We're getting paged for a bunch of seemingly unrelated metrics, and apparently the app is completely broken for the Plus store, and they churn.
Well, this seems pretty bad, right? Our app is not able to handle large bursts of webhooks. And if you're developing for the Shopify platform, this is a fixture. This is a reality. If you're listening to product webhooks, there will be a lot of them. So we've hit our fifth major problem, and it's a big one. So let's take a look at what is actually happening in the system. First, like we said, we get that influx of webhooks. And what our jobs are doing, or what the web servers are doing, rather, the first thing they do is validate that these are webhooks that we care about and that there's actually work to do based on them. We're going to check things like, is the product still valid? Is it something that the merchant has configured to sync to the marketplace? Is the shop still in good standing? Are they paying their bills? Is all of that in order? All of these perform hits to the DB. And while they're all relatively innocuous calls, none of them are particularly expensive, suddenly making 50,000 of them in a second actually causes a whole bunch of load. And we start to see some real contention on the DB layer. What we aren't going to talk about here is database tuning. We're assuming that you've done some due diligence here, you have the right indices in place, and the problem is not artificial bottlenecks on your DB, it's a real bottleneck on your DB. So this contention on the DB and this slowdown actually ripples very quickly throughout the entire rest of the system. Everything that touches the DB is affected by this. This impacts the web server cluster, any merchant traffic that's coming through there that needs to hit the database, and it impacts the worker server cluster. All of those background jobs that are trying to sync products, effectively, nothing is really working. What we can't do here, as I mentioned, is control the rate of those webhooks. Merchants installing and us needing to keep up with their data means that we have to be able to handle this load of webhooks. So we can't fix the problem there. What we'll do instead is apply a simple principle to how we handle these webhooks, which is basically just the web servers are not allowed to touch the database at all when processing a webhook. This means that we avoid that additional potential bottleneck and ensures that we can respond to Shopify as quickly as possible. All we're going to do is make sure that we write the data that we need into the queue, respond to Shopify, and move on. With this new principle in mind, let's look at how traffic flows through our app now. Merchant requests are behaving pretty much as normal. The merchant traffic is not programmatic, so it's not prone to that same burst of tons and tons of traffic. It's OK to make database calls from our merchant traffic. And in fact, it's very important in order to be able to properly render your front end. So that's all still unaffected. What's different here is that our webhooks are now skipping all of those validation steps that we talked about earlier. This means we're writing a lot more into our queue because we're pushing that work down into the worker cluster to decide what actually needs to be done. What this means is that we're putting way more load on our queue, and that concept we talked about earlier of storing minimal data and ensuring those payloads are as small as possible is really critical, because now our queue capacity is a really bounding metric of our app. If we were just storing full payloads, we would blow it out very, very quickly. It's important to note that we're balancing a bunch of different performance characteristics here. There's a lot going on. We're trying to avoid contention on our database by putting more work on our queue. This has worked really well for us and with our topology. But again, like with most things in this talk, you're going to need to consider what your architecture can sustain and where those trade-offs are for you. The other thing we talked about is storing as little as possible in those job payloads. If you take it to an extreme, this might mean you need to make API calls back to Shopify to retrieve more data when you actually do the processing. This means you need to balance your Shopify API rate limit against your queue capacity and against your database contention. This is somewhat of a delicate balancing act, and this is probably one of the areas of the talk where the nature of your app and your problem domain is the most important, where you're making these trade-offs. If your bottleneck is the Shopify API rate limit, you can try things like batching or using our new GraphQL APIs to buy yourself a little bit more room here. Again, what's important is to find what works for your app. So for us, that means no more database calls and ensuring that those minimal jobs are going into our queue. This allows us to ensure a very speedy response time from Shopify. We're never going to be failing webhooks. We're going to avoid all of those retry spikes. And now we can handle those plus shops. So things are looking really great. This is a big hurdle for us, but we've overcome a huge architectural challenge, and the money's starting to flow. Marketplace is really happy with us, and they're starting to think about their IPO. But we notice over the next couple weeks that the trend of our background queues just seems to be ever growing. And what this means is that each individual job is now spending much longer in the queue. And what's happening is products are taking forever to sync to the platform. Instead of minutes or seconds to sync your products, it's now taking hours or even days. And to a merchant that's trying to respond to a trend in the market or price their products competitively, having the price not sync for a day can actually mean real dollars are lost. We're starting to get bad App Store reviews again. Things aren't looking as good as we thought.
Imagine a large store rebranding. The first thing they're going to do is they're going to go to the Shopify App Store. They're going to go pull an app that lets them modify every single product simultaneously for those changes that need to be made. Cool. They get it, install it. And the first thing they're going to do is they're going to re-watermark every single image. They're going to remove the old one, add the new one, upload all the images. And each of these product updates will spawn a webhook. Bam, 50,000 webhooks. Now, we just talked about this. We can deal with 50,000 webhooks. But we're still limited by the rate limit. We can't just throw servers at the problem and clear our queue. We can only go as fast as we're being allowed to go. So while we make a start on that queue, the merchant's still got the app open. They're going to update all the titles, maybe add the store name in front of them. Bam, 50,000 webhooks. Well, still got the app open. Maybe we should add some SEO metadata. Got to find the products. Bam, 50,000 webhooks. And while the merchant that's doing this is almost certainly not expecting a real-time update, there are a few that will, let's be honest, but most of them are understanding. What about the little merchants? The one with 1 to 3 products, who just updated their price, and that update is now stuck in a queue behind 150,000 updates. This is our final problem, slow syncing. And let's revisit our throttle. We're spreading the jobs out over a longer period of time. That's essentially what a throttle does, to make sure you stick inside your rate limit. And this is giving our largest stores, of which by now we have quite a few, plenty of time to stick duplicate data into our queue. And because this is governed by the rate limit, as I said, we can't just throw more worker servers at the problem. We need to drill deeper. Let's look at the anatomy of a job. Now, we've got multiple worker servers and multiple copies of a job. This means we've already had to worry about concurrency, and our app has already had to deal with this. Concurrency, or race conditions, is what happens when 2 worker servers pull the same product at the same time, especially if in one case we have 1 job for a title update and 1 job for a title update plus the SEO. You want the correct one to go through. And you can't always guarantee, even with first-in, first-out queues or whatever you're using, you can't always guarantee this comes out right. So what we're going to do is, or what we are doing, I should say, is we're locking it. When we start processing a product, we lock it, say, don't touch it. Then we do a bunch of processing, and then we unlock it again. We're still, as well, we're running a lot of duplicate jobs, which we don't need to run. Like, this queue shouldn't be 150,000 products. Really, we only have 1 upload to do with the finished version. We don't have 3 uploads per product, we have 1. So what we're going to do is, when we receive a webhook, instead of trying to actually queue a job to process it, we're going to queue a job to mark it as dirty, essentially doing the lock bit of it up front. And then we have a clock, a cron, scheduler, whatever your language calls it, that runs a sweeper job periodically that picks up all the dirty products and uploads them all at once. We nickname this a mark and sweep architecture. And it gives us 2 sources of jobs. We have the webhooks, pushing the mark jobs in, and the sweeper pushing the much more expensive processing jobs in. Let's go back to the job and have a look at it. The mark is now a separate job, very lightweight, and, most importantly, not affected by the rate limit. This mark is still duplicated. Nothing we can do about that. We did just get 3 webhooks. But because the mark is no longer rate limited, because it is not processing, we can just throw servers at the problem. We can just ramp our worker cluster through the roof and just keep getting those dirty jobs marked as quickly as we can. The sweeper is now guaranteed to never have to do duplicate work, because all it's doing is saying, at the current moment in time, find me everything dirty, and I'll process it. Most of the work is being done in the sweep. Like, fundamentally, what your application is usually in the sweep. It's all the API calls you make. So this makes it the most likely spot to be the primary source of DB contention and API calls. Which means that if we use environment variables on the sweeper, we can control the entire operational behavior of our application. Let's say, for whatever reason, we get a huge sustained spike of traffic, and we don't know where it's coming from, and we can't really see, we don't have time to try and figure it out. And those mark jobs are actually getting to a point where they're stressing our database. That database contention issue is starting to crop up. What we can do is, as a first step, don't sweep as often. We just said the sweep is where a lot of your work's going on. Don't run it every 2 minutes. Run it every 15 minutes for half an hour until things die down. Maybe don't try and process every single dirty product if there's going to be 1 million dirty products in the queue. Process the first 5,000 of them. It lets us change our load pattern entirely. But there's an even more important aspect to the sweeper, in that it solves our first problem. We can guarantee fairness. The way we architect our sweepers is we don't say take every dirty product, because in a lot of cases that gets very big very quickly. We take the first few. But we can take the first few for each pending shop. It lets us enforce the fairness across so that that big merchant is no longer drowning out the smaller merchants. Their 10 products are going to go through in the first batch. And the merchant with 150,000 updates is maybe going to have to wait a little bit longer. Obviously, if your entire business model revolves around the merchant with 150,000 products, maybe you give them a little more thought. But for us, as like the Shopify channels, we have to be somewhat equal. This sweep lets us adapt to handle most operational situations with just an environment variable tweak and then an app restart. And it buys us, again, time, because when you're being paged, time is the most critical thing, the time that lets you work out what's wrong, the time that lets you debug things. And this buys us time to actually solve the problems. We're now using mark and sweep to remove duplicates. And this implementation is very, very, very application specific. Make sure it works for you. Don't just drop it in because we told you to. And the principles are the most important thing behind it. Fairness, not doing duplicate work. With this in mind, let's review the changes to the architecture.
So this is where we started. It was very, very simple. We had, as you know, a basic web server and a database. The web server was doing everything. It was handling webhook traffic and merchant traffic, and it was performing any API calls that needed to be happened to perform those product uploads and handle all of our business logic. What we want to stress here is that this actually wasn't bad. This was actually the right way to start. When we're building a new app and we aren't sure about our market and we aren't sure if there's a fit, starting with the smallest possible thing is actually exactly what you should do. Now, some of the principles like horizontal scaling and rate limiting, maybe that should be baked in from the start, but you can find the right balance for you. What's important is that starting small and growing to your scale is actually the right approach. So for us, this is where we've grown to. We now have a web cluster handling our webhooks and our merchant traffic. The merchant traffic, as I said before, it's doing what it needs to do to render the front end. It's hitting the DB. It may make marketplace API calls as infrequently as possible, but if it needs to. The webhook traffic, on the other hand, is going straight into our queue and ensuring as fast as a response time to Shopify as possible and ensuring that we can sustain that throughput. Our clock, or our cron, is now pushing those larger sweeper jobs that are doing the bulk of the work in a highly configurable fashion so that we can control the runtime performance implications of our app. The worker cluster is now throttled to ensure that we don't blow out our rate limits, and our API traffic has circuit breakers to protect us from downstream outages. These principles have helped us scale our apps for some of them to as many as hundreds of thousands of active merchants, and we hope that you can apply some of them in your own apps as well. We're now going to take questions from the app, so if you've already asked them, I will pull it up. And if not, again, the code is unite and find track 1. Thank you. All right. First question. Let's talk about your resiliency and availability. You mentioned you use Redis and Sidekick. How do you ensure that Redis is highly available? What happens if Redis fails? So this is actually not really a question for our team, because building at Shopify, we actually have the luxury of an entire amazing production engineering team that handles a lot of these complexities for us. So I think that this is a great question, and I would love to be able to answer it for you. The reality is I don't actually know the answer. We rely on some people I see over there in the crowd. If you want to find out more, you can go talk to Dale. Do you have anything to add, or is that?
No, pretty much. Like, if we did answer, we'd be guessing, because like we don't deal with that day in, day out.
It's a very good question, though, and it is really important to think about how your back-end systems that you depend on are highly available and ensuring you're covered from outages of everything you depend on, not just third parties. All right. You mentioned that webhooks shouldn't hit the database direct, but how is the job queue stored in memory? Isn't that volatile? So our job queue is backed by Redis, so we're not actually storing it in memory. We are still depending on a third-party system. In our case, Redis is designed for this very, very sort of high throughput, low contention, write-heavy traffic. So it's not in memory. It is still a persistent store, but it's just one that's much more designed to handle this high degree of traffic. Also, the fact that it's a separate system from our database means that any problems with Redis, like any problems there, would be isolated from the rest of the app as well. I think the upvoting kind of changed the order of these, so let me... With all of the moving pieces in your final application, how do you monitor this in production? What metrics do you observe, and what tools do you use? So we use, again, a lot of this. The nature of these questions is that a lot of it we get for free from, again, our awesome production engineering team. But the sort of tools we use, we rely heavily on Datadog. We use StatsD to push lots of metrics to Datadog. One thing we do, which I'll admit is a bit of an anti-pattern, is we monitor the state of our queues from our background jobs. So that's actually something I'd like to see us move away from, and I advise you not do this. But basically, like, we actually have background jobs that report performance metrics to Datadog, and what happens is when our queues get bogged down, our performance metrics start failing. So that's not very good.
I'd also add, like, a lot of the time when you're monitoring, it's actually really important to monitor on business metrics, not necessarily application metrics. Sure, your database might be at 80%, but that isn't necessarily a problem. The important thing is what the problems your application is actually experiencing defined in the terms of the users of the application. So a lot of the time, if you write your pages and your monitors based on application metrics, you'll get a lot of false alarms. You'll get paged a lot, and maybe you like getting paged a lot. I don't, but I try and. But if it's you get paged when people are experiencing problems, then you know it's always a real issue, and you know you need to do something to resolve it. That's the only thing I'd add to that.
OK, so the next question. Would you suggest deferring webhook HMAC verification down to the workers when making sure that webhook handling doesn't touch the database at all?
We HMAC verify in the web, but we don't touch the database. So we have some HMAC stuff that doesn't touch the data. I'm pretty sure. Might be remembered.
Yeah, again, we don't know the answer to this because we don't write that stuff. The stuff that's doing the HMAC verification for us is coming from gems that we build on. We may in the future look at making some of that stuff available to partners as well, because we do really want to, like, part of us developing these apps against the platform is so that we can learn where the pain points are and help make that help reduce friction to app developers as well. So yeah, in that case, we're relying on libraries that do that HMAC validation. But yeah, I don't believe there's any actual database hit.
There's no database, definitely no database calls.
Yeah. Why does webhook break even though we are sending out a 200 OK response to Shopify API that we received this webhook? OK, so in the case where we were talking about webhook failures, our app architecture was actually failing, which was causing us to not send those 200s. So you're absolutely right. If you're sending the 200s to Shopify, you're fine as long as you're actually retaining that data and doing something with it. But yeah, as long as you send the 200s, you're all good. You're not going to see those failures. What's the best way to process? What's the best way or process to transition from Angular to React? Any thoughts?
Carefully, no. Honestly, what we're transitioned from is server-side rendered. So for those of you that are developed in Rails, you render your HTML on the server side, and you have very light bindings on the controller side, on the client side, that actually does the work. So we're doing the transition from server-side to React, which is actually, in a way, a lot simpler, because one side has an app, the other side doesn't. The other side's flat code. So you can deal with them completely separately. We do use beta flags, things like that. So typically, we put them on a per shop level. A shop will have a beta flag. If this flag is enabled, the shop gets experience 1, else it gets experience 2. And then you can, if those are stored in the database, you can easily just add it to your own dev shops. and it lets you roll things out gradually. So it means that when you're developing, you're not having the whole thing being developed in a side branch and merging it all at once. You do actually just have both states existing at the same time under the feature flag. And then when you're ready, you just roll out the percentage of stores that have that feature flag. Then when it's at 100%, you remove the flag entirely and delete all your code.
OK, we build apps for Shopify Plus. Should we build it within Shopify admin panel or outside Shopify? Some UI elements are not supported by Polaris. So obviously, our goal is to make our app ecosystem as consistent as possible, and we would strongly encourage you to figure out how your problem domain can fit within the Polaris design language. So, I mean, that will always be our recommendation.
Yeah. Yeah.
When will the dummy frame be released? Will it work for POS also?
OK, skip it.
Oh, OK. Do you plan on developing an ideally Twitter Bootstrap-based version of Polaris that could be used with the typical Ruby on Rails stack without React?
Last session? Are we done with last? Are we on last session?
Is all of this the last session now? Maybe I missed it. Changes to the A's.
OK, cool.
We're out. OK.
Are there any questions from the audience?
Yeah.
Oh, yours is still in here? I just archived it then. Hold on. Let me find it. Oh, they're all in here. OK, that's...
Do we have a mic or anything? Oh,
Yeah.
OK. You want to...
Do you want to go?
Yeah.
Sure.
What's that? Somebody in the
No,
audience?
someone in the crowd.
OK, so we're
We're
just
going to get
bringing
you a
the
mic.
up.
And then
and then you can ask it.
Sorry? The question was, do we use tools for rate limiting with Sidekick? We don't actually. The way that we handle it is we actually put jobs into the queue at a to ensure that it processes slower than the rate limit. Yeah.
Yeah, we keep our some of our throttle information in Redis as well. So to make sure it's highly available, we write the current rate limits into Redis and read them out as a separate layer that's not necessarily touching the others. That's kind of where that's going for.
Yeah.
Why are you moving away from?
Sorry, OK.
Why are you moving away from server-side rendering in favor of client-side rendering?
Honestly, it's a bigger topic. It's where the industry's going, everything like that. I guess. Yeah.
I think the biggest thing is just to provide more seamless interactions to merchants and better perceived performance, better perceived response times, that sort of thing.
Yeah.
It also makes it a lot easier to do things like when Joe was talking about having a concept of pending in the interface. It makes it a lot easier to seamlessly refresh things when stuff is complete, that sort of thing.
Yeah.
You can obviously do it with server-side rendered stuff, but making the whole front end more dynamic just makes that easier.
You're using circuit breakers on the outbound. Do you use anything like bulkheads on the inbound, or do you handle that with load balancing and auto scaling and
Load balancing and stuff. We don't use we're aware of it, but we don't try and solve the problem until we need to. And right now, because we've put so much emphasis on not touching the database, writing straight into the queue, things like that, we haven't hit a traffic problem that's bad enough to need that. But yeah. I think we're running a bit low on time here, so if you have any more questions, please feel free to find us afterwards. We'd love to talk about this stuff, right?
Yeah, seriously, we'll be around. There's a break coming up now, so we'll probably mill around here if anyone wants to talk more in person. Thanks a lot.
Thank you.